Hello all, we will continue for state space representation. Now we will talk about state controllability. A system is completely controllable if there exists an unconstrained control input u of t, which is the input for the system u, that can transfer any initial system state x of t naught to any other desired location, can transfer any state from its location to another location in finite time t between t naught and t capital. Now we will see this example. You can control x1 and transfer it x1 dot to, and transfer it to x1, and can transfer x1 to y, but cannot access x2 and transfer it to x1 dot or x2 dot, as there is no connection between u and x2 dot. If we follow the arrows, we will see that we don't have any direct connection between u and x2 dot. Then the states x2 and x2 dot, state x2 and the derivative cannot be controlled, or they are uncontrollable. But for state x1, it will be controllable state. How we can mathematically check the controllability of the system? We can check the controllability of the system by obtaining the controllability matrix, which is consisting of B, then AB, A square B, and A power two B until A power n minus 1 times B, where n is the order of the system. We will have the power smaller than the order of the system by 1. The system will be state controllable if the rank of the matrix C or the controllability matrix equals the system order, which is n. Now we will see an example. Consider the system given below: the A matrix, this is the B matrix, and this is the C matrix. We will construct the controllability matrix CT, which is equal to AB. The power of A is smaller than the order of the system by 1, where the order of the system is second order. The size of A is 2 by 2, 2 rows and 2 columns. Now we will construct the controllability matrix B, which is 1, 0, and AB, we will multiply the A matrix by B. The A matrix is negative 1, 0, 0, negative 3 times B, row times column, negative 1 times 1 equal 1, plus 0 times 0 equals 0, where it will be negative 1. And for the second row, 0 times 1 equals 0, and negative 3 times 0 equals 0. Then the AB matrix will be negative 1 and 0. As we see here, negative 1 and 0. We will construct the controllability matrix 1, 0, negative 1, 0, and get its determinant. The determinant equals positive 1 times 0, which is equal to 0, and negative times negative 1 times 0, which is also 0. Then the determinant of the controllability matrix equals to 0. Then the rank of the controllability matrix is smaller than n and not equal to n. Then the system is not completely state controllable. We have some states of the system that we cannot control using the control input u. Another thing we have to know, which is state observability. A system is completely observable if and only if is the only condition for being completely observable. there exists a finite time t, such that the initial state x of 0, we can obtain the initial states x of 0 by using the previous observations of y. If we have the previous observations of the output, we can obtain the initial states x of 0. Given the control input, which is u, for time range between 0 and t capital. Therefore, from the figure, we can see that x1 is observable from the previous values of y. Also, x1 dot can be observable, but for x2, which is not connected to the output, cannot be observed from the previous values of y. Also, x2 dot cannot be observed from the previous values of y, then these states are not observable or unobservable. How we can check observability mathematically? We have to obtain the observability matrix, and the observability matrix is equal to c times a, c a square, until c times a power n minus 1, where n is the order of the system and the power of a will be smaller than the order of the system by 1. The system is called or is said to be completely state observable if the rank of the observability matrix equals to the system order, which is n. Now we can see another example to illustrate the observability check. X dot equals A matrix times X plus B matrix times U, and Y equals C matrix times X. The observability matrix equals CA, where the power of A is smaller than the order of the system by 1, where the system order is second order. Now we will obtain or construct the observability matrix. C equals 0. For CA, we multiply C times A, multiply the row by the first column. 0 times 0 equals 0, 0 times 4 times 0 plus 4 times 0 equals 0. Therefore the first value equals to 0. For the second value, we multiply the C matrix by the second column of the A matrix. 0 times 1 equals 0, 4 times negative 2 equals negative 8, then the second entity is negative 8. Now we will construct the observability matrix C 0 4 and CA 0 negative 8. We obtained the determinant of the observability matrix, which is equal to positive 0 times negative 8, which is 0, negative 4 times 0, which is equal to 0 also. Then the determinant of the observability matrix is equal to 0. Therefore, the rank of the observability matrix is not equal to n or smaller than n. Therefore, the system is not completely state observable. We have some states in the system that we cannot observe from the previous observations of the output y. Another example for your practice: check the state controllability and the state observability of the following system. We are given the matrix A, matrix B, and matrix C. We have to check the state controllability and the state observability. Now we will move on to another topic, which is eigenvalues and eigenvectors. Eigenvalues of matrix A are the roots of the characteristic equation, which is lambda I minus LA determinant equals 0. The eigenvalues are the specific values of the system which determine the poles of the system. Consider the following example. We have the A matrix 0 1 0 first row, 0 1 0 0 1 second row, and negative 6 negative 11 negative 6 the third row. we determine the characteristic equation, which is lambda I minus LA. Then we will subtract lambda minus the diagonal elements of A. Lambda minus 0 equals lambda. Lambda minus 0 equals lambda. Lambda minus 6 equal lambda plus 6. And the off diagonal elements, we will opposite their signs. 1 will be negative 1, 0 remain 0, 1 will be negative 1. And for 0 will remain 0, 6, negative 6 will be positive 6, negative 11 will be positive 11. Now we have to get the determinant of this characteristic equation. The first column is positive, second column is negative, and third column is positive. We get lambda times the subdeterminant, which is lambda negative 1, 11, lambda plus 6. And for the second entity will be negative 1, and we remove row and column with negative 1 and have the submatrix or subdeterminant 0, 6, negative 1 and lambda plus 6. We get the characteristic equation lambda cube plus 6 lambda square plus 11 lambda plus 6 equals to 0. We can factorize this equation to obtain the eigenvalues, or use the calculator mode equation to obtain the roots. The factorization will be lambda plus 1 times lambda plus 2 plus times lambda plus 3 equals 0. Therefore, the eigenvalues of the A matrix are the roots of the characteristic equation lambda I minus LA determinant will be negative 1, negative 2, and negative 3. When we equate this equation to zeros, we obtain negative 1, negative 2, and negative 3. An example to illustrate eigenvalues calculations. Find the eigenvalues if k equals 2, m equal 10, and b equal 3 for the mechanical system we have obtained before. X dot v dot equals 0, 1, negative k over m, negative v over m times x and v plus 0, 1 over m times f of t, which is the input force. This example will be given to you for practice. Now we will proceed to similarity transformation. What is similarity transformation? We are required, or we have to transform one state space to another state space model. This is achieved using what is called similarity transformations. Now we consider the state space. We know x dot equals ax plus bu and y equals cx plus du. We need to transform this state space model to another state space model, which is x hat dot equals a hat x hat plus b hat u, and y hat equals c hat x hat plus d hat times u. We have to obtain the new matrices a hat, b hat, c hat, and d hat from the given state space model matrices A, B, C, and D. The vector or state space vector we need to obtain, or we need to reach, represents the physical state relative to some other reference. It is the relative or state space relative to another reference or system, or another coordinates, mathematical coordinate vector. When the coordinates are transformed to another set of coordinates with the same dimensions using algebraic coordinate transformation as the transformation known as similarity transformation. This transformation is known as similarity transformation when we transform one set of coordinates to another set of coordinates with the same dimension. The mathematical form that change the variables is written as: we have the states of the system at the current state coordinates equal transformation matrix times the required state space or states of the new reference coordinates, where T, the transformation matrix, is a non-singular matrix which is having the size of n times n rows and n columns. Therefore, we can obtain x hat by multiplying this equation by T inverse from the left. We obtain x hat equals T inverse times x. This is a relation between the transformed state space and the current state space or states of the system. We can use this equation x hat equals T inverse x by taking the first derivative of this equation, then x hat dot equals T inverse times x dot. We substitute x dot by ax plus bu. Then we substitute x by T transformation matrix times x hat. Then we multiply T inverse inside the brackets. We obtain T inverse A T x hat plus T inverse B times U. Now we have T inverse AT is equal to A hat in the new state space model, and the T inverse B is equal to B hat in the new state space model. Therefore, A hat equals T inverse AT and B hat equals T inverse B, the new matrices for the new state space representation. And now we will consider the output equation y hat equals C hat times x hat plus D hat U. Now we can substitute x hat by T inverse x. Then C hat T inverse equals the C matrix. Therefore, C hat equals, we can multiply both sides by T from the right and obtain C hat equals CT, and for D hat will be equal to the D. The outputs are the same and unchanged. Y equals y hat. Therefore, the equation of y, which is Cx plus du, we can compare the coefficients. C will be equal to C hat T inverse. Then we obtain C hat equals CT and D equals D hat. Therefore, we have obtained all the new matrices for the new state space model. Then the relations to perform the transformation of coordinates algebraically, we have A hat equals T inverse A T and B hat equals T inverse B, for the C hat equals CT and the D hat equals D. For the transformation to a diagonal system, we have to memorize some properties from linear algebra. If a square matrix A can be called diagonalizable if there exists an invertible matrix P, which can be inverted, such that P inverse times A times P is a diagonal matrix. If we have an invertible matrix B where P inverse AP equals a diagonal matrix. For an n by n square matrix is called invertible, can get its inverse. Also non-singular. Non-singular means it has a determinant. Its determinant is not equal to 0. If there exists an n by n square matrix B such that A times B equals B times A equals identity, where B is the inverse of A. Any matrix multiplied by its inverse we will get the identity matrix. What are the main properties of diagonalizable matrices? First of all, it's easy to handle. We can use this matrix with easy way. Their eigenvalues and eigenvectors are known. Also, we can raise the matrix to a power by raising the diagonal elements entities to the same power. If we want to raise the matrix to power 2, we only have to raise the diagonal elements to this power or to the power 2. The determinant of a diagonal matrix is simple, the product of all diagonal entities. If we want to get the determinant of a diagonal matrix, we have to multiply all the diagonal elements by each other. Now we will see an example. X dot equals 1 matrix A, 1, 2 for the first row, and negative 1, negative 4 for the second row times X, plus B matrix 1, 0 times U, and Y equals 1, 1 times X. Find the eigenvalues, eigenvectors, and diagonal form of this system. First, we obtain the characteristic equation, which is lambda I minus LA. The system is second order system, or the A matrix is 2 by 2, 2 rows, 2 columns. Then the lambda I will be a 2 by 2 matrix, lambda 0, 0, lambda minus LA 1, 2, negative 1, negative 4. We subtract each element by element. Lambda minus 1 equals lambda minus 1, 0 minus 2 equals negative 2, 0 minus 1 equals 1, lambda minus 4 equals lambda plus 4. This is lambda plus 4. Then we have lambda minus 1 times lambda plus 4. We for the first value, and the second value negative times negative 2, it will be positive 2 times 1 equals positive 2. Then we have lambda square minus lambda plus 4 lambda, then plus 3 lambda, and negative 4 plus 2 equals negative 2. This is lambda square plus 3 lambda minus 2. This is the correct equation. For lambda 1, we obtain the values of lambda 1 and lambda 2. Lambda 1 will be 0.5616 and lambda 2 will be negative 3.5616. These are the two roots of, or the two eigenvalues. Now we have to get the eigenvectors. For the first eigenvector, we will call it P1, which is equal to P11 and P12. And the second eigenvector will be P2 with entities P21 and P22. To obtain the eigenvectors, we multiply the A matrix by the eigenvector equals the eigenvector multiplied by the eigenvalue. For the first eigenvector, A P1 equals P1 times lambda 1, the E matrix 1, 2, negative 1, negative 4 times the P1, which is P11, P12 equals P11, P12 times lambda 1, which is 0.5616. We have two sets of equations. We multiply the first row by P11 and P12. 1 times P11 equal P11 plus 2 P12 equals 0.5616 P1. And for the second row, negative 1 times P11 will be negative P11 minus 4 times P12 equals negative 4 P12 and 0.5616 times P11 or P12. These equations are dependent. We can assume P11 equals 1 and get P12. P12 will be equal to 0.216. Therefore, we can call P1 equals a constant A, which is the multiples of 1 and 0.216, where A is not equal to 0. For the second eigenvector, A, P2 equals P2 times lambda 2. The A matrix times the P21, P22 equals P21, P22 times the value negative 3.5616. Then we have the two sets of equations, the two equation sets, negative 3.5616 P21 and here negative 5616 times P22. These two equations also dependent. We can assume P21 equals negative 1 and obtain P22 which is not equal to negative 1. And then P2 will be equal to a constant B or a multiple P times negative 1 and P the other value. Therefore, we will obtain the eigenvectors or the transformation matrix. The transformation matrix is equal to the eigenvectors 1 and here 0.216 and here we change negative 1 to the new value. We have the state space model for the system and we need to obtain the new state space model or the new coordinates. We obtain the the A hat matrix, which we call A1 equals T inverse AT, where it will equal T inverse times A times T will be 0.5616 and here negative 3.5616. The B matrix will be 2 and 1, T inverse times B, and C, the new C matrix or C hat, this is B hat, and C hat matrix will be C times T, where we multiply C times T matrix and obtain the C hat. Now we have the new state space model 0.5616 and here negative 3.5616. And also we need to recalculate B and C matrices. This is the new state space model and we now have finished this example and finished the second part of state space modeling. See you in the next lecture. Goodbye.